introduction. Okay. Yeah, so the session is going to be recorded for all of you, and I will now share my screen. And do you see now my screen, everybody?
Yes, I at least I see it.
Okay, perfect. And okay, and now I guess it's also in big full screen, right?
Yes.
Okay, perfect. Then as said by Martina, today what I'm gonna present, it's a follow-up of the first talk of the series, but I'm gonna focus into the parametrization of the cirrus cloud particles PSDs, especially paying attention to the small particles. As an outline for the talk, I will first introduce the PSDs and also the motivation of our study. And I will explain a little bit in detail the normalization method that we used to obtain the parametrizations. I will also introduce the in situ database that we use in our study, that's the Julia database. And after that point, I will just do a short recap of what I have presented until then. So then I can talk about the different parametrizations and also present results comparing one mode or two mode parametrizations. And finally, then conclusions and the outlook. So PSDs, also called the particle size distributions, it's the concentration of ice crystals as a function of their size. Here in the lower part, you can see two examples of two single PSDs, where you have in the vertical axis the concentration and in the horizontal axis the size. And PSDs are fundamental for understanding clouds because they contain information about the history of the cloud. So PSDs that are from a recently formed cirrus will look different from the PSDs of an already aged cloud. There would be also differences depending if homogeneous nucleation is taking place or only heterogeneous nucleation. And there will be also difference depending on the temperature. So as I said, PSDs contain a lot of information. They also determine microphysical and radiative properties of clouds. And the knowledge of the PSDs allow also to compute cloud properties, like, for example, the total number concentration, ice water content, or the effective radius that it's quite used for obtaining optical properties. This can be done by computing moments of the distribution. And also the PSDs are key for retrieving cloud properties, both microphysical and optical, from the remote sensing instruments, and they are also used as input for climate models. PSDs, studying them, it's challenging because, as you can see here in this figure, the sizes of the ice crystals, there's a wide variety of shapes, and there's also a wide variety of sizes that changes with temperature, and it also changes with location. And also having different instruments that will have probably different processing algorithms will result in obtaining slightly different PSDs. So because of all this complexity, when one wants to use the PSDs for the retrieval of remote sensing instruments and also for models, one then needs to make use of parametrizations. One example of parametrization used for retrieval from remote sensing, it's in DARDAR. For those that haven't heard of DARDAR, this is a combination of measurements from the cloud profile radar combined with the LiDAR Calliope. And the aim is to retrieve profiles of ice clouds properties. This DAR, so the framework doesn't give number concentration, but provides other properties, like, for example, reflectivity, extinction. There's also effective radius, but still not number concentration. And the focus on number concentration and why it would be useful to have also this retrieved is because number concentration is often used in climate models and in numerical weather prediction models as a prognostic variable to predict the evolution of clouds and also to estimate the radiative effect. So there's this work from Sogdeval et al. In 2018, where they use the framework of Dardo to obtain the number concentration. This framework aims at constraining parameters of the PSD, and they use a parametrization that for now I will call DO5, and I will explain a little bit more in detail later. And some of the results of this study can be seen in this figure, where again we have PSDs with vertical axis concentration, horizontal axis the size, and this is for different temperature ranges. And we see in black the mean PSD for the observations, and in red we see the mean PSD of applying this parametrization, this DO5 parametrization, to the observations. And one of the main things that we can see is that between 20 and 100 microns for warmer temperatures, there's an overestimation between a factor 2 and 3. And this could be because parametrizations typically until now have been obtained using databases that didn't include particles smaller than 50 or 100 microns. And this then leads to incorrect estimations of the number concentration. So with this in mind, what we wanted to do is check this DO5 parametrization in an in situ database that actually includes very small particles, to see how well then this parametrization would reproduce the PSDs. We also wanted to see how the retrieval of the number concentration could be improved, and if this improvement could be obtained by, instead of using one mode, as is the current one, to use two modes. For that, first, I need to introduce the way this parametrization was obtained. And this is by using the so-called normalization method that consists basically in scaling the observed PSD to find an underlying universal distribution. And using then this universal distribution, it's possible to reconstruct the observed one. And the way of scaling then the PSDs is by using moments of the observed distribution. This normalization method was first applied to raindrop size distributions, and typically one needed to assume a shape for the distribution. There's here I also write some other frameworks. One that it's currently being used, it's this one by Field et al. 2005-2007, and this method consists in using one moment of the PSDs to predict the PSDs and then relate moments using power laws. And as I mentioned before, then, for example, this parametrization was obtained using databases with particles larger than 100 microns. Another framework is the one by Testud et al. This is still for raindrops. The one of Field, it's also already applied for ice crystals. But going back, sorry, to Testud, what they did was normalizing using the liquid water content and the mean volume radius without knowledge of the underlying universal distribution. And then this framework was adapted by Delanoy for ice crystals. And again, the parametrization that they obtain, it's also using particles that are larger than 50 microns. This last method, the one by Delanoy, it's the one that we will use in our study. And this method, to explain a little bit more in detail, what aimed is to provide this universal normalized function that it's valid for temperatures lower than 0 degrees, and that would also be applicable for different locations. The first thing that we need to do is to refer to the equivalent diameter, that is then the diameter the ice crystal would have if it was a spherical water droplet of the same mass. And in order to compute the equivalent diameter, we need the mass dimension relation. In the study from Delanoy, they used one from Francis and Brown. And in our study, we used the mass dimension from Kremer et al. 2016, which later in 2018 was also compared to several mass dimension relationships, and they show good agreement in cirrus clouds. So now that we have the equivalent diameter with the mass dimension, the next step would be to compute moments. In the case of this method, the interesting moments are 3 and 4 that are computed from the in situ PSDs. And these moments are chosen because these are the ones that define the normalization coefficients. So one is the mean volume weighted diameter, or DM, that is the ratio between the fourth and the 3 moment. This coefficient DM, then it's used to normalize in the size space. For normalizing in the concentration space, what we use is the N0 star, also called the intercept parameter, and it also uses the 3rd and 4th moment. So then what we do is obtain this DM and N0 star for each single PSD, like the ones that I show at the very beginning, and we obtain then the normalized PSD. And what Delanoy saw when doing this is that all the normalized PSDs have a similar shape. And they saw that this shape could actually be fitted to a function that they found could be a modified gamma distribution. The modified gamma distribution is defined by 4 parameters. So one would be the N0 star, and the other one, the other parameter depends on the M. So these are specific for each PSD. But then there's the alpha and the beta parameter that would be fixed. In the first study in 2005, they defined the alpha and beta just checking a few combinations and checking which one was better when retrieving different quantities. And in 2014, actually what they did to obtain the best alpha and beta was used what is also done in the method by Phil. So that is using a square linear regression, and they defined a cost function. This cost function should fulfill a condition that it's being defined by 2 variables, one that is sensitive to the small particles, so that is proportional to a low moment, and another one that is sensitive to larger particles and therefore proportional to a larger moment. So one check here random alpha beta pairs, and the one that gives the minimum of the cost function, then it's the chosen pair to define the modified gamma distribution that would fit all the normalized PSDs. As an example, you have here the results from the Lanois. So in the left side, you have the observed PSD for different campaigns. And then on the right side, you have the result of applying the normalization. As you see, the shape of the different campaigns is similar. There are some differences that they argue it's related to the microphysical processes, but in general now all the data is concentrated between the 0 and the 1.5, and there's also some changes in the tail of the distribution, and this goes with the temperature. So for the coldest temperatures, then this tail disappears. In their studies, no, they have then 3 parametrizations. So the one that I already introduced, the DO5, it's the one that is currently used in the Dardan retrieval, and also the one used for the estimation of number concentration bias of the val in 2018. And then there's the D14 and DARDAR, that these are from the latest study from 2014, where they, the difference with the previous one is that here they use this cost function to obtain the best alpha and beta. And the difference between the D14 and the new DARDAR is the mass dimension relation that they use. So please keep also in mind these 3 parametrizations, because I will come back to them later. As I explained, for this normalization method, it's common to use also an in situ database. In our case, the database that we are going to use is the Julia dataset that was compiled at the Research Center Jülich, and it includes information about clouds. We focus on the cloud data, which includes 11 campaigns covering from tropics to the Arctic. And one of the main differences with respect to the databases used in the past is that it includes very small particles down to 3 microns. During these different campaigns, as you can see in the figures, there's also different aircraft involved. There's also different instruments. So there's spectrometers, there's cloud imaging probes, there's light scattering sensors, and all the data has gone under very strict quality checks. For example, the scattering effects were taken into account. And about the secundariized production, that was very important for the mixed phase clouds. Since we are into the cirrus clouds mostly, we don't pay attention to secundariized production. As said, the main focus is then on the ice particles, so it's going to be mostly in the cirrus clouds. Here, as you can see, the analysis include temperatures lower than 250 Kelvin. Here, there would be some mixed phase clouds, but for temperatures lower than this, it's considered that most of the particles of the water droplets would be already glaciated. So then one important point about the dataset, as I said, there are several instruments. And as I mentioned also, some of the challenges when using PSDs is each instrument is going to have a different size grid, and then the PSDs are going to look different. So there's this work by Martina Kramer and Nicole Spelten. It's in preparation, and what they managed to do is to obtain synchronized size bins to represent the data from the different instruments in logarithmically equidistant beams that then would be looking the same for all of them. And then this makes the comparisons and the analysis way much easier. So now I think it's the time for the recap. Because of all the information, what we want to do is obtain a parametrization that allows also to obtain better results of number concentration. For that, we are using, on one hand, the Julia database that includes the very small particles. And we are applying to this database the normalization method from Delanoy. This normalization method consisted in computing moments, the measured in situ PSDs, normalized in situ PSDs using these moments, and then because of all the normalized PSDs having a similar shape, then finding this function that would apply to all of them, in this case, a modified gamma distribution. In the study from Delanoy, they use the extinction and reflectivity, but in our study, we are using physical parameters of the ice water content and the number concentration. So the condition of defining the cost function to find these best alpha and betas, using quantities that one is sensitive to large particles, in our case is the ice water content, and another one to the small particles, that would be the number concentration. It's follow also in our definition of the cost function. So the first thing that we want to do also is to check this DO5 parametrization in the Julia dataset. And here in the next slide, you can see the results. So this is similar to figures that I've already shown. So again, we have PSDs, vertical axis concentration, horizontal axis is the size, and this is for different temperature ranges from -90 to -30 degrees. What we see in black is the mean observed PSD from Julia, and in red, what we see is the result of applying DO5 to the in situ database. So the red is the parametrization. In our case, then what we see is that there's a general slightly underestimation for the very, very small particles. And what is in agreement with what was also shown in the previous study by Soteval 2018 is that for the warmer temperatures where V-modality starts playing an important role, we see that for particles between these 20 to 100 microns, there's an overestimation. So when we apply them to the Julia dataset, the normalization process explained, we see something similar, or like we see what we were expecting. So we see this similar shape for all the campaigns. These are just some example with the tropics and mid latitudes and a mix between mid and high latitudes. We see again that the data is mostly focused between 0.5 and 1.5, and we also see the variability in the tails in this gray area where it gets smaller also for the colder temperatures that would be here for the tropics. So we see that we also have a similar shape, so we can also continue and obtain our best alpha and beta parameters using the cost function. Here now we have the summary of the parametrizations that I will present. The first three you already know. These are the ones from the literature, from Delanoy. The next two, these are the new parametrizations obtained with the Julia dataset and with the cost function defined by the ice water content and the number concentration. And these are, as the ones in the literature, one mode. And the last four, this corresponds to two-mode parametrization. So we have one parametrization for the small particles, smaller than 50 microns, and then another mode for the larger particles that is larger than 50 microns. And the difference between the RAN and log is that for the log version of the parametrization, what we are using in the cost function is the logarithm of the ice water content and the number concentration. sorry. Here in the next slide, you see again single PSDs. The observed one would be the ones in black. This is for different temperatures. So we have around 200 Kelvin and around 234 Kelvin. And the first row correspond to all the one mode parametrizations, and the single row correspond to the two mode parametrization. What we see is that the one mode parametrization, at least the ones from the literature, have difficulties in capturing the decrease of the concentration here. The new ones have a very different behavior actually, and the ones that seems for now to fit quite well are the ones with the two modes. But in order to have a better view of which one fits better, what we did was taking then these single PSDs and then do the difference between the parametrized and the observed PSD. And those results are then here in this slide. So these plots correspond to the median of the difference of the single PSDs. The upper left plot corresponds to what would be the new parametrizations. We have in pink and light green the two modes, and in comparison to the new one mode, they are closer to the zero line. In the middle upper plot here, we have a comparison between all the one mode parametrizations again, being the red, blue, and dark green, the ones from the literature. And actually we see that the new ones do not improve for the very, very small particles. For the large particles would look the same. And then the upper right plot, this corresponds to a comparison between the parametrizations of the literature, and then again in light green and in purple, the new two-mode parametrizations. What we see is that mostly for this area between the 20 and the 100 something microns, there's the overestimation that we saw, it's reduced. And for the very small particles for lower than these 10 microns, the main improvement would be seen if we look at the plot in the lower row. So these plots are again medians of the single PSD, but in this case, I'm including the 1 sigma in shadow. And if we look to the green, light green, and to the purple colors, we see that the variability of the reconstructed PSDs for these very small sizes is reduced. So it seems that for the very small PSDs, the main change when using the two modes is that the variability is reduced. And now I want to focus a little bit in this region here. And for that, then I'm applying again just the same plot. So again, the median of the single PSDs, but in this case for different temperature ranges from -90 to -20. What we see is for the coldest temperature, for these larger particles, there's not much difference. It's again when the modality starts to play a role for the warmer temperatures, when the improvement is mostly seen in this area. So then the two modes improve the reconstruction of the PSDs between 20 and 100 microns for temperatures warmer than -60 degrees. If we now have a look at retrieval of the number concentration and also the ice water content. What we have here are correlation plots. So for all plots, the vertical axis corresponds to the parametrized and the x-axis to the observed. If we focus now first on the upper row, this is number concentration. In the first upper left plot, then we have the DO5 parametrization, and the other two correspond to the two bimodal parametrization. And well, we have them here in black, the one-to-one line. There's also a regression line in red, and these dashed red lines is just the regression line moved a factor of 2. And then this, the ellipse, would correspond to a 2 sigma. And what we see, the main difference is that actually the spread, so we look at the ray region, is reduced when we use the 2 modes. And also, if we have a look at the root mean square error, it decreases from 0.33 to 0.21. So the main thing that we see is that the spread is reduced. I also wanted to have a quick look at the ice water content. And here what we see is that all the parametrizations deliver very similar results. And what we see is that in general, there's an underestimation for the lowest values and an overestimation of the larger. But the consideration is also that there's not much change because the ice water content is more sensitive to the larger particles. And as we've seen, there's not much change in the very large particles between parametrization. I wanted just quickly to have a look again to the number concentration, but in this case, going again by temperature ranges. So we have in the upper row, this corresponds to the DO5 parametrization, and the lower row corresponds to the two mode parametrization. What we see is that for the coldest temperatures, there's not much change between the parametrization, which is similar to what we've already seen in the reconstructed PSDs, so no surprise. And the change comes then again when we have a look to the warmer temperatures, especially to the very warm -30, -20 degrees, where we see large deviation from the one-to-one line. Whereas for the two mode parametrization, it stays more or less constant. Also, if we look at the spread, the same conclusions, the spread is reduced when using the two modes. And also the root mean square error, even though for both parametrizations, it increases with temperature. For the DO5, it goes from 0.29 for around -60 degrees to 0.52 for the warmer temperatures. And in the case of the two mode parametrization, it stays around the 0.20. So this, as I said, then the two modes performs better than one mode for higher temperatures. And this leads into the conclusions of my talk, where we have that the two modes parametrization improves the reconstruction of the PSDs for sizes between 20 and 150 microns for temperature between -60 and -20. Also in this temperature range is where we see the larger improvement of the number concentration. And what we see for the very small particles is that applying the two modes, what does is reducing a little bit the variability of the constructed PSDs. For the ice water content, all parametrizations deliver similar results. And now the question would be, how feasible is it to implement then a two-mode parametrization in the retrieval algorithm? And this was all. Thank you very much for your attention.
So, Irene, thanks a lot for your nice presentation.